All right. Hi everybody. So thanks for joining me for this third lecture. So our goal today is to continue the discussion of R-matrices and quantum groups, and as you can see on my screen, the relation between R-matrices and quantum groups is the relation between the chicken and the egg. So it's if you have the full-fledged quantum group Hopf algebra, then if this Hopf algebra has this co-commutation relation, then there will be an R matrix. But the route that we would like to pursue today is the opposite. You start. It's easier in the and also historically in development of the subject. It's first came the R matrices and then came quantum groups, and so in what we do, it's easier to construct the R matrices, and it's easier to start from there. And then we would like to see how this how starting from we construct them geometrically, then analyzing them, we can deduce the quantum group action. And so and maybe again by as a metaphor, maybe you can compare the role of the braiding as encompassed in the R matrix with the role of DNA. So that's I don't mean it too seriously, but something maybe you should. It's an analogy. Maybe it's worth pointing out. And so we will. So what we already started last time, and we'll continue today. We have a collection of R matrices. That is to say, we have our starting point. Starting point is a collection of R matrices. So we start some collection with first the spaces in which they act. So maybe some kind of Mi of A, and this you can think of this you can think as a vector space. You can think of the vector space, or more ambitiously, maybe it's a free module over there's some ground ring, and you have adjoint polynomials in A, something like that. Some other functions in A you want to consider, or maybe polynomials, or depends on something like that. And so where K could be some ground ring, like maybe Z adjoint this deformation parameter H bar, something like that. And what of course would all be in reality, what this will be in for us, this would be some cohomology, by which I mean it's either ordinary covariant cohomology, or maybe a covariant K theory, or a covariant elliptic cohomology, and that's a covariant of some space X. So the action would be this construction would be really geometric, and this variable A is really a variable in some torus, which sits inside the automorphisms group of X. So that's the real meaning of this variable A. And then this collection of vector spaces, we have collection of matrix operators, which we denote by something like this. So maybe we draw a picture like that. So that's so maybe M1 of A1, M2 of A2, and then there's this R matrix that puts them so this operator in the tensor product that satisfies. So it's an R matrix that satisfies the Young-Baxter equation. which you can see behind me. Oh, sorry, not behind me. It was the last lecture. You could see it behind me. And so from this, we would like to construct. We would like to make this. We would like to make all these modules, all the spaces to be modules over some quantum group. And the way to do it is the following. So, which already kind of explained last time. So first we extend this R-matrices and to things like you take kind of ordered tensor product of some modules mi, maybe sorry, m ki of some variables ai, and so if you have one such collection, and another, so this would be li of di, then we just define the R matrices to be a product of R matrices for individual factors, something like that. So, and then this also satisfies Young-Baxter equation. That was step one. And step two, we define operators. So we would like to define operators in this space. So in a space like this, by taking matrix elements in, so this is, we draw a better picture here. So this is the space where we would like to here. This is maybe physical space, what people call it. And this you designate, this you call auxiliary space. And you take matrix elements in this auxiliary space. So you get, so this, in other words, this is an R matrix is a endomorphism of a tensor product, and in one factor you can take matrix elements, you get operators in the other factor, and then those would still depend on variable on maybe we rename the auxiliary variables, maybe we call these variables A, and this variables U, so that to designate their auxiliary role. And then we'll also, and then, so take matrix element to get an operator here will still depends on this variables UI, and then take whatever set, take, and so this is an operator valued with functions in UI, and you can take whatever, an arbitrary linear functional, or maybe values in UI or any other linear functions, such as derivatives. Or you can also you also have the freedom not to take any linear functionals, but just leave it as is, leave it as a generating function for operators. And so so this clearly an algebra, because the composition is just, so composition such operators, you just take more, so by multiplication you define by and multiply two such operators, you just put more of them in the auxiliary space. That's the composition of operators. But also co-algebra. Also, there's a co-product, also co-multiplication. By saying, well, how can I make two operators out of one? Well, I compose my R-matrices like this. And so then if I take one matrix element, I get two operators. So this rule actually needs discussion, so maybe a little bit of a discussion. This needs a bit of a discussion. If my modules MI, maybe if the dimensions of this MI is infinite. So this is of course, if I take matrix element of a product, if my matrix was of a finite size, then of course this would be a finite linear combination of matrix elements before. But if the matrix was of infinite size, then it will be in principle an infinite linear combination. And what would be convenient for us? So this is, I recall that our modules MI, so maybe modules just M, just some typical module M. This is, like I said, it's some cohomology, some space X, and there will be two features of M apparent in this description. So this would be this module will be graded with grading bounded below. And the way it will be apparent is that our space X will be in fact a disjoint union over some spaces D over D. Maybe I'll put, or maybe K. So just K, let's say non-negative X K. And so this would be, so it will be trivially just cohomologies of different pieces will be different graded pieces, and this grading will be different, will be bounded below because just the space is empty after. And so, for example, e.g., so maybe have an example in mind, like if I have, so the simplest example where when we want to construct if you're interested in UH bar of GL2 hat, this space XK, this would be the cotangent bundle of the Grassmannian of k-dimensional subspaces in some n-dimensional space. This is some n, or maybe some fixed, so maybe some fixed n-dimensional space, I'll write it like that. And I apologize, for my ground field, ground rings, I sometimes write C, sometimes write K. And if we're interested in physical application, typically you're interested in this varieties as complex manifolds. So maybe I'll write C and here. But the theory doesn't matter if it's the complex manifold or not a complex manifold, or some Grassmannian over some arbitrary field. So so this is k-dimensional subspaces in some fixed dimensional space, and then even if the space is infinite, that is still, if you're studying k-dimensional subspaces, the space is empty below zero. So you cannot study. You can study zero-dimensional subspaces, and that's where things end. There's nothing left. Or if we're talking about the quantum version of GL1 hat and then another hat, an example of a space K could be the Hilbert scheme of k point in C2. So this means ideals in the ring of polynomials of two variables of codimension of finite codimension, and in fact this codimension k. Again, that codimension is bound. I mean, has to be non-negative. And so this is and then R-matrices will preserve this grading. And so for the simple reason that R matrix will be some geometric operation, and this geometric operation will be difficult for that geometric operation to go to some different connected component. And so then when you take matrix coefficients, you can what you can do is you can first you can start when you take matrix coefficient, you can first if we take graded vectors here and there, so we take in other words we take graded pieces. If you have an infinite dimensional vector space, but we take the matrix coefficient, we take them in the graded pieces, then this would be a graded operator in the other channel. So one can define graded matrix elements to define the quantum group that we want. But then, of course, you have to be prepared that in principle, so this co-multiplication, this in principle that would be, so when you multiply two infinite matrices and there's this grading will tell you what? Will tell you that your co-product is in principle an infinite sum, but an infinite sum of terms, each of which acts locally nilpotently. So each of which is the action of this. In other words, this infinite sum acts. Its action is well defined in your highest weight category, but in principle, the sum is in principle infinite. So this co-multiplication in principle it will in principle send this algebra to not its tensor square, but a tensor square completed in the sense that you allow infinite combinations, but the combinations are such that they kill a vector of any given degree. So that's what and so maybe so example. So this would be we will have depending whether we will work in Euclidean homology, Euclidean K-theory, or elliptic homology, we will get R matrices that depend on your spectral variable as a polynomial, or I mean somehow this. Remember, remember we had this trichotomy that our variable A could be sending in the additive group, or the multiplicative group, or maybe elliptic curve. And if we just want to focus on this part now, so this is this, then the corresponding quantum groups are called Yangians. This are called Yangians. And for this, the R matrix will have the property, so then the R matrix will have a good expansion at the variable u going to infinity. So if I take, so we will look at the expansion. This variable u, it's in the additive group. This will be going to infinity of the additive group, and the first term of the expansion will be 1. Then the next term will be something what's called classical R matrix, so something called R over U plus O capital of 1 over U square as U goes to infinity, where R, the connection with the Lie algebra, is that this R will be this canonical element. So this sits in symmetric square of some Lie algebra G. This is a Lie algebra with an undegenerate invariant Balayan form. And so that Lie algebra could be decomposed as, so we can write it as a Cartan subalgebra plus the sum over all roots. This could be there could be in principle an infinity of roots. So this is how we get infinite sums. So there could be, so in principle there's the set of roots could be in principle infinite. And then there is some root subspace G alpha. So that root subspace is finite dimensional. And G alpha is dual to G minus alpha in this decomposition. And so this is again, since there's infinite sum, it's completed in a certain way. So and so then what would be the coproduct by this rule? What would be the coproduct of each EI? So we take what we're interested in, the coproduct of each EI. We want to compute. So first question, I want to know the coproduct of EI. Want to know what that thing is? Well, what would that mean? That means that we have to take a product of two R matrices like this, and so then we take the coefficients. We're interested in the coefficient of 1 over U, the 1 over U coefficient. So this means the coefficient of 1 over U. Is additive, right? So if we multiply two matrices and we extract, so to define the coproduct, we first need to find some matrix element which gives us this EI in the other channel. So maybe we want to compute EI, then means we have to put kind of some matrix element that kind of acts as a dual vector here. So here will be EI. And then when we compute the coefficient 1 over U, we get a sum from here and here. So that means the coproduct of EI is EI tensor 1 plus 1 tensor EI. So this means in particular, the R matrix commutes with that, because the R matrix is supposed to put it in the opposite order. And so the opposite order here is the same, and so it means R matrix commutes. And so this means R matrix is invariant. In other words, R is G invariant. Right, but we have so that's good. And then the next, but we wanted to see an infinite sum appear, and so let's see that. Let's look at this. Suppose we decided our module M is a module of highest weight, so maybe or lowest weight, let lambda in M be a lowest weight vector of weight lambda. That is to say, G alpha acting on lambda, this is 0 if alpha is less than 0. And also, if I have an element H acting on lambda, this is lambda of H times lambda. This is where H is in the Cartan subalgebra. And so then let's see what am I going to get for the matrix element of this lowest weight vector. So maybe here I get here I put different colors here. Here I'd like to apply this to this lowest weight vector. I'd like to take the corresponding matrix element, so that again the coefficient of lambda. And so what is that going to be? So this would be saying that so if I expand this R matrix, this particular matrix coefficient, so maybe I'll write it like this. So R, and so you start with the vector lambda, and you end up with the vector this, and then the corresponding, the other two entries are free. So that's my matrix element here. Well, it starts with 1, so this would be so it starts with 1, not so interesting. Then the next term, by my rule, will be minus, like lambda by because I have my invariant bilinear form, and linear form lambda defines me an element H lambda. Right? This is the summation. This is summation lambda of Hi times Hi. So if I have a linear form, then by bilinear I get this over U. So H lambda over U. Okay. And then there'll be some next term. Let's call it H lambda 1, kind of the next brother of U square. So this is a deformation. This is a deformation of T times H lambda, because we're in our deformation, we're deforming the algebra. We're deforming is the universal evaluating of G adjoint polynomials in T. Remember, our Lie algebra were maps from some group to the Lie algebra G, and so this is this is T's. So these are maps from my additive group to G. And so so geometrically, what this guy records geometrically, maybe I'll give this away since it's important. So this really acts. So this is, I told you that the Cartan sub that our modules geometrically are weighted, are graded just by the like a connected component, and in fact, these connected components are specified by the way to geometrically specify the connected components geometrically is to say that those are just the ranks of some universal bundles. Like, for example, over Grassmannian, there's a universal bundle, which is over its fiber over subspace of the subspace itself. And you want to say, well, the K in the Grassmannian of K-dimensional plane is the rank of that bundle. Similarly, over the Hilbert scheme of points, there is a universal bundle, namely the quotient of the whole ring by ideal, and number of K is the rank of that bundle. So this geometrically this act by integers, which is just the rank of some universal bundle. And then its older brothers, this act by the first Chern class of that same universal bundle. So if I have a universal bundle, I have a Sealy operation which just records its rank. It's an operation which is on every connected component would be just a constant and given equal to that rank. But then I get a non-Sealy operations, namely I can put all the Chern classes of that bundle, and this would give me this kind of older brothers of my Lie algebra elements in. And so we would like to now compute what would be that the coproduct of this element here. What would that be? Well, to compute this, we need to draw this diagram. And I can't form any consistency as to coloring of these diagrams, but I hope you're not too confused by it. And so here I put my matrix element I want. Let's say this, and then well, like we're gonna get something. Now from this I have to take, and then we take the coefficient of 1 over u squared. And so okay, well, how are we going to get the coefficient of 1 over u squared? Then one term would be if, well, we get u squared from here or u squared from there. So the coproduct of this H1, this would be either this, it appears in the first factor, or it appears in the second factor. This is, or this is now to compute other possibilities. And when I take then I have to take a 1 over u coefficient from one vertex and the 1 over u coefficient of the other vertex. So let me just do it right here. So if I compute 1 over u coefficient in every place, then I'm gonna get. No, let me draw a better picture. So here I'm going to get some EI and then EI. Here I'm going to get EJ and then EJ. And so what I need to compute is I need to compute the matrix coefficient of, I need to compute lambda EJ EI. Right. All right. And let me to make it a more kind of a more closer to more traditional notation in Lie theory. Let me do it slightly different. Let me call them E alpha. Let me call E, maybe do minus alpha E alpha. Bearing in mind that the weights, the given root space may be more than one dimensional. So, but let's just pick some particular basis in the root space. So maybe E beta minus E beta. So I need to compute you put, well, let's call this minus alpha here, beta there, E minus beta there. So now I need to compute, maybe more familiar, E beta E alpha acting on the highest weight. And okay, well, we know right away that this is going to be, what's it going to be? It's going to be 0 most of the time. So it's 0 unless, first of all, this is a vector of some particular weight, and so this is an operator of some particular weight. So we're going to get 0 unless the weight of this operator is really 0. So it means unless alpha plus beta equals 0. But also this vector is annihilated by alpha if lambda is less than 0. So it means, and then alpha is less than 0, or it has to be positive for this to be non-zero. And if it is non-zero, then when we know that the commutator E minus alpha E alpha, this is minus H alpha, and so that means we're going to be minus lambda alpha times, well, this vector is 1. So if alpha plus beta equals 0 and alpha is bigger than 0. And so this means this sum here, this would be this extra sum. Move it here. So it means this extra sum I'm going to get here is summation over alpha. Maybe put minus here. Then lambda alpha, and then I get like R minus alpha, means this is a canonical element in G minus alpha tensor G alpha. So this is now I remember that this root space could be more than one dimensional, and so that means I have to sum over bases, so I get just this kind of alpha part of this R matrix. So again, it's in principle an infinite sum, but this infinite sum it's going to act by 0 on a vector of any given weight eventually. Right? So this is the action that will define. So this coproduct goes to completion, and the completion is such that it acts on it acts on modules of lowest weight. Right? So maybe a remark. Right. So there's somehow 2 remarks. Is that so usually number 1 is usually the condition that the R matrix commutes with the coproduct of my Lie algebra G is 0, and that the R matrix so this was a trivial thing we derived, and then the slightly non-trivial thing is that the R matrix now is supposed to, if I take the R matrix of this coproduct of this H lambda 1 R inverse, that is now supposed to put this in the opposite form. So this would be the opposite coproduct, and the opposite coproduct is where you exchange alpha and minus alpha here. So these are both linear. Those are both. So maybe I'll write it like this. These are both linear equations on R, and so usually these equations determine R uniquely. multiple. So this is now if you want it, so meaning that if you're computing, making some geometric computation, and you geometrically defined your R matrix R, and you'd like to know what it is. Okay, you construct it geometrically. There are many things we can construct geometrically without understanding too well what is the actual answer. Then means you can. This means if you understand. Sorry. Means if you understand the two things, if you understand what is the Lie algebra involved, and how do first classes of the tautological Chern bundles, so for the first Chern classes of the tautological bundles, how do they co-multiply? That's usually enough to determine the whole R matrix. And so an example of that. Example of that is that if I have remember I had this Hilbert scheme was associated with when the Lie algebra itself was GL1 head, and so in this Lie algebra we have operators, called kind of traditionally called alpha n with commutation relation, alpha n, alpha m. This is n times delta n plus m, this sort of commutation relation, time maybe some central element. So this is central. And the R matrix has the form, there's some diagonal part plus summation over n alpha minus n. And so what this bilinear, so we get like bilinear expressions in these three bosons, and so then these bilinear expressions, what this bilinear expressions in alpha n, what they should remind you of, the Sugawara construction, Sugawara formulas, Sugawara-like formulas. Well, maybe Sugawara is an overkill here, since I'm doing the simplest loop group here for the Virasoro algebra, the algebra. And in fact, this kind of older brothers, that is the Virasoro. And the condition, and this condition here, what this formula here becomes, this formula here just means, this means that the R matrix is what's called the Liouville reflection operator. So this from very few things, from this bosons. These are kind of Nakajima operators on the Hilbert scheme of points, and then you need to know a little bit more, namely what the first Chern classes of line bundles do, and so that's a generalization of length formula. All right, so now we continue. What was my next maybe a slightly extended example? And so then this is the end of the slightly extended example. And then so we have defined an algebra, and so I think so this is obvious. It's obvious that the original R matrices do give a braiding. The braiding of this module in the category of the modules of right. So because if I want to know how to put, if I want to put two modules in an opposite form, well, I might achieve this by Young-Baxter. I can achieve this by putting them in the original form and squeezing them. Well, R-matrices are unitary, so I don't have to worry about overcrossing or undercrossing. It's just a crossing, and so I can put them in this form. Sorry. So this means if I want to know what's the product in the opposite way, well, I just use the R matrix. Also, everything. This is maybe a general remark. So this is good. Also, if we read it, so every formula we write, if we read it, we can read it kind of a mirror reflection. We can exchange the role. So I wonder if there's a way to do it. So let's see. I didn't practice this part, but maybe let's see if my sorry. What did I accomplish? Nothing. Let's see if can I okay, right. It's hard to read, but the meaning of that is clear, right? So then if we use it, we can use it in auxiliary space. Instead of the physical space. Right? Meaning instead of braiding in the space where we want it to act, we could braid in the space where we take the coefficient. And so that means the Young-Baxter is both the commutation relation and co-commutation relation. More generally, so if I have any, so this is the braiding is an example of a morphism in the category that we constructed. So we constructed somehow we constructed the category. Tensor category. And this has to be taken with a grain of salt. So modulo poles see below. This will be this is actually think what we, because we started with modules which were polynomials over variables AI, and we now started acting by matrices which are rational in this variable. So we, strictly speaking, leave that category, but let's not worry about this for now, because we could, like, for example, if we're constructing a finite dimensional quantum group, then there is no spectral parameter. All our matrices are invertible. So we can, okay, let's measure this situation. We constructed a tensor category in which the objects are this tensor products of the spaces. And morphisms are maps that commute with R-matrices. Maybe schematical the way to think about it. So if I have a morphism, you can think of some sort of black box. Or sorry, it's not black, it's blue, but it'll be maybe acting from tensor product of 3 to tensor product of 2, and that guy commutes with the R matrix, meaning that if I put the R matrix here, or I put the R matrix there, these two things are equal, right? So these are the maps I want to consider. And now I'm saying that every such morphism gives me also relation. Every such morphism also gives me also a relation in my algebra by that same procedure that I can take this picture and I can flip it. So now it tells me that 3 matrices. So now it's a relation between. Now it acts in this blue space, and it's a relation between operators here. So that's very nice. That I think would make this would be, I think, some description like this would really make somebody like Hermann Weyl very happy, because the point of view of Hermann Weyl, maybe, which I really liked. One of the many points of Hermann Weyl which I really appreciate and really liked when I was young, is that if I think of the some reductive group inside some vector space GLV, then this is there's a kind of better, you can alternatively think about of all operators, G-invariant operators, from V to some power K to some power L. Think about the group as the same as think about invariants. So this is to say, these are invariants of my groups in mixed tensors, so in tensors that have so many covariant and contravariant indices, and that is the same as to have a group. So then I can, if I know all invariants in particular, I can reconstruct the equations of the group. So that's kind of like what's happening here. So this is really kind of maybe the main point of Hermann Weyl's book about invariance, if I may say so. So and then well, okay. So now we need to find a way to actually construct our matrices, and for this will be a little bit so how to actually construct. All right. So this is so construction. So this is R-matrix is a you can place the R-matrix in a slightly more general discussion, namely how we would be thinking about constructing. So R-matrix is an example of homomorphism in this category. So this is insert. So let's see. Try to. I apologize. So. Sorry, I'm having a technical difficulty here, which I'll hope to. So this is R-matrix is an example of this. It's an example where you have two inputs and one output. So in particular, so an R-matrix is a special case where you have we're ignoring what's happening here. So here comes the in and out, and then inside the cross. This is a special case. And so this is the beginning of a discussion that we're going to have in more detail at some later point. But maybe it's useful to know that this is after all we're talking about this module was supposed to be. So this, and what's sitting here was some cohomology of some space X, and then there's this cohomology, or K-theory. So maybe I'll write K-theory. This is just shorter, current K-theory of some space X, and here current K-theory of some space X prime. And this were both moduli vacuum in some quantum field series. And so the way to really think about this object is to think of this as this is really what brings them together. That is really some interface. Between these two. So this is like the particular for the R matrix. You can imagine a situation where you have we had your maybe different color. So we had our Riemann surface, which let's see, green. So the space-time, and we had some quantum field theory living on that. There's some fluctuations. So maybe I'll just draw some. Some sort of stuff fluctuates. Some fields fluctuate. And then, but then you can imagine your space is also sits in an external field. There's some parameters of your theory that vary. So then there's some variation of parameters. So across your space, there's a variation of parameters of your quantum field theory. So this would be the case for the R matrix. And so in particular, you can have a situation where something critical happens. So as you cross some boundary, there's something else, some critical phenomenon, some kind of critical point. And then before and after that critical point, before that you sit in one kind of modular vacuum, and then after that you sit in some other kind of modular vacuum, and then there is at the critical point there is more. There's some kind of new. There's some in the interface. There's some new physics here. There's some new degrees of freedom that include both the degrees of freedom that come from here, the degrees of freedom that come from there, and they're somehow live together. So maybe a general principle you can ask, well, if your physics depends on a parameter, then the richness of your theory is always semi-continuous. There's always more physics at a special point than it is at a deformation. So you can always there's always more massless particles, more more fluctuations there. And so this you think, well, what this has to do with anything? But what I'd like to say is that the way we're going to construct the R-matrices, the scenario that we're going to construct the R-matrices, is that you should imagine that we really kind of have like a line of possible tensor products, and then here on one side you have one tensor product and one, and you should think of this as a line just with really where this A1 over A2 lies takes. So this is an element of that group G in which your spectral parameters sit. And so then here you have one kind of tensor product. So maybe I'll write it like that. Here you have the other kind of tensor product. So meaning that well, you can either take the opposite, or you can let's just put them in the opposite order. It's not essential. It's just bookkeeping. Let's put it in essential. But then at a special point, there's something new. There's something new. There's some critical phenomenon here. There's some water boiling. More physics or more math here, and that critical point would be something when you have some particular value of these guys. And so it means what you associate to this space, you associate some larger module. So maybe let's call them, let's call, I don't have such a good notation for that, but let's take like a tensor product. It's kind of two. This is not a symbol in common use. It's just my invention for this particular lecture. So and so that what we would like is both of this to actually embed here. So they both embed. But the and the co-kernel of this embedding, of either embedding, is, well, if I say torsion, is that everybody understand this meaning? Is torsion. Means it's a module annihilated is torsion with respect. So this is a free module. This is a module over polynomials in A1 and 2. It's a free module here. It's a free module here. And this is also a free module. But this embedding is an embedding that has a co-kernel. That co-kernel means annihilated. By some power, like some expressions, like when you just write maybe h to some power and then to some large, something like this. If this is this bad point, that means this something like this will annihilate this module. And so if you have this, then then this means this addresses the following concern, is that we started with a category of module in which the modules were polynomials in some variables AI, so we didn't need denominators there. But when we write the R matrices, then we get rational functions, and so then we have to somehow account for poles. And the way to account for this poles is that in fact there is an enrichment of the tensor operation. There is in fact this other tensor product which is symmetric and which is kind of better. But it's the difference is that this is the ordinary tensor product in two different ways. They embed into this they embed into so that it's not an isomorphism. It's isomorphism after, means if you divide by expression like this, if you introduce poles, then it's an isomorphism, and then you get an isomorphism between this and that. So that's and so what would be the this scenario where you get a map between free module with a torsional core kernel? That's a very kind of that thing here, that when you had this kind of this is a very typical scenario. In a Ukrainian homology. We're going to talk about it more. And so but let me, of course, we're going to talk about it at length, but let me illustrate it by so this kind of 25 side, so the kind of a kindergarten illustration. Yeah, this is in fact something like yeah, sure. This is even more. This is, I think the way to say it is like well, anyway, there are many fancy names one can assign to this. So a kindergarten illustration. Suppose I have my x is a point with a trivial action of the multiplicative group. Let's just talk. Yeah, so this is an element. This is an element, has an element A. And if I study the current K-theory of X, well, what's it going to be? I have, this is the point, I'm really studying representations of this group, and so this is just the character of this representation, just polynomials like that. Right? Now I can consider Y, which is A1 or C. Well, let's just C, with, again, with an action of C star, which is defining action. Then this maps to X, right? This is a projection to X, and the pullback with respect to this, very easy to see, is an isomorphism. Gives pullback gives an isomorphism. So the current K-theory of Y is also the same thing. In other words, any C-star covariant vector bundle on C is trivial, and we only need to specify how Cx and the fiber over 0. So that's the specification. But now we consider a different map. Then there's a push forward. push forward from equivalent K-theory of X to equivalent K-theory of Y. Right? And so this its image is we have to look at what is generated. Its image generated by the structure shape of the origin. Namely, you take that's the prototypical torsion shape. It's something which is annihilated by one minus. So it's just annihilated by X, right? And so that is to say, so that's my structure shape of the origin. This is where my generator for covariant K-theory of X goes. And this is by definition the quotient. I take my polynomials in the coordinate X. This is the coordinate. And this is, well, this is a quotient by X times by the ideal generated by X, right? So let's have this exact sequence. And so in my ring here, this corresponds to this coordinate. So okay, maybe this coordinate. This coordinate here has weight with respect to my A equal to A inverse. That's first and like a first thing when you do representation theory. And so in linear algebra we teach students that all vector spaces of the same dimensions are the same. But then once we start representation theory or algebraic geometry, then we'll tell them that no, if I have a dual representation, that's in general very different representation. I have a dual vector bundle, that's in general very different bundle. And so if I act on my space with some weight A, then the action on functions is by the dual representation, so by A inverse. And so that tells me that my structure shape tells me that if I consider this exact sequence, it says that K theory of Y, which is so this is the generator of this K theory. It's a trivial bundle, and that says that this K theory of Y, which is the Y, which is an A, maps by 1 minus A inverse to K theory of Y. Sorry. So this is assessed, or maybe this says that the Cook. So, okay, maybe you can. So this says that the structure of the origin is in a covariant K theory is 1 minus A inverse of times the structure shape of C, right? That's what I'm trying to. This is what this formula means. Means that the co-kernel of the map, means that the co-kernel of the map, you take the equation, the push forward in here, that is torsion, right? That is Z of A plus minus 1, precisely mod out by 1 minus A. That's the sky. So that's the So a typical, in other words, this is a super typical situation. If you think of that this map here involves something like a push forward, then this is typically would have this feature, have the co-kernel distortion. This will give us this precisely the rational dependence of the R matrix on the parameter. And okay, so this is what's the kind of key example. Well, that arrow just means the generator goes to so the generator of this goes to this sheaf. That's what it means. The image is generated by this guy. So maybe let's do the key example. Namely, we have to find UH bar of GL2 head action on like a current K theory of spaces like, let me abbreviate the spaces. You put XN, right? Where XN is the disjoint union over all K, T star of Grassmannian K-dimensional subspace of the, okay. So in particular, X1, well, this is not a very interesting space. We're talking about Grassmannian of one or zero-dimensional subspaces in a one-dimensional space. So it's just a point union a point, and so we need to if you look at my notes. Right. And so what we need to, and so then of course the K theory, the current K theory, so of X1, and I have to say what the current variables are. We will take the action on this, on the Grassmannian, we'll take the action of, maybe we denote the variables A1 through AN. This is an element in GLN that acts naturally on here. And then we have one variable that scales the cotangent fibers, that is scaled by, so that's consistent with other places, has to scale by the inverse. So there's one more variable called H bar, scales the cotangent fiber. But anyway, the action here is trivial, so I get just two copies of, take the ground ring, which is H plus minus 1, gives kind of A1 plus minus 1. You get two copies of that. Right? And so now we need to have a map from this and this space. I abbreviate. So quantum groups usually write like C2 of A1. I understand this ring is very different from C2, but let's just, so we need two different maps from C2 of A1 tensor C2 of A2, and then the other way around. Just write the opposite tensor product. They have to both go to the K theory of X2. They have both go into here. Right? So what is X2? X2 is, well, there's always there's a cotangent bundle of Grassmannian of zero-dimensional subspaces, so it's a point. And then there is a cotangent bundle of T star P1. This is Grassmannian one-dimensional space and two-dimensional space, and then there's a point. There's not so many things we're going to be able to do about the point, but we can think about T star P1. So that T star P1, what is going to look like? So we'll have this base P1. So this is my picture of T star P1. So it has the base P1, and this base has an action. So maybe. So this is my P1. Has points 0 and infinity, and I have an action of my torus. Well, depends how of course, it slightly depends how I identify this action, but up to conventions, maybe let's say it acts with weight A1 over A2 in the tangent space here, and then the opposite weight A2 over A1 in the tangent space at infinity. And then I have the cotangent directions. So this is my picture of T. So maybe it should be this pink. So it's the T, the cotangent line at infinity to P1. And then there's a cotangent line at 0 to P1. And then here I have, here's my weight has to be the opposite of this. So it's A1 over A2 and then divided by H bar. And here is the opposite of that. So A2 over A1 and divided by H bar. And now here I have to map. So here I need to go like two. This is a four-dimensional space. I have the middle, so this has by weight. This is the composition actually. So this is like a. If you look at the weights, this decomposition is by the weight of the Cartan. Cartan subalgebra. As I told you, this is the Cartan subalgebra remembers the rank of the tautological bundle, and that this is this decomposition. And so I have to have this space has two vectors of weight 0. Well, it depends how you normalize the Cartan. If you normalize the weights between 0 and 1, or maybe more traditional between -1 and 1, so that it has one vector of weight -2, two vectors of weight 0, and one vector of weight 2. And so these are I have the two vectors of weight 0 have to go here. And so what I would like to have is I would like two different maps. So I need two different maps from the K-theory, the current K-theory of 2 points. I need to have two different maps to the current K-theory of T star P1, and then a different one. And what I will do is I will factor. So I will factor this map geometrically into two things. One would be, so two things I could do is I can study the attracting or repelling locus with respect to my so after all I told you that this line here is the line of kind of A1 over A2. And so A1 over A2 going to infinity or going to one end of the group or the other end of the group means I can study attracting or repelling locus with respect to these two directions in my group. So I have, maybe I'll take a copy of this. If my A1 over A2 goes to 0, then which points have, then the following points have a limit, namely I have to take points that sit here. This is the kind of attracting, this is the attracting set. If A1 to A2 goes to infinity instead, then the attracting points would be this point. And you can think about it also slightly differently, in that the T star P1 is resolution of the singularities of the quadratic cone. And that my T1 and T2 will act on it so that it will have one of this. So this is my A1. My A1 over A2 will act on this so that the points that it's either one line on that cone or the other line on that cone is has a limit, as either one goes to infinity or the other. And so then what you're looking at is you're looking at the pre-image of the set under this resolution. And so one part of this picture is that this would be this push forward from the covariant K-theory of attracting manifold. This is attracting as A1 over A2 goes to say 0. And then similarly, there's a push forward from the other side. But what we need to supply is so this is a map that will have that torsion co-kernel that we want. And this is an isomorphism that we will need to supply. This is an isomorphism. So this will need to supply. The fact that this is abstractly isomorphic is not enough. We need to have an R matrix. What we need is an actual map from actual isomorphism of this space to this space. And so then you have, in other words, in this picture, so this is being kind of the fusion of the two different representations. I know what the images of this maps are abstractly, that I know. What I need to supply is the actual isomorphism of these spaces onto their image. And so that's what we will need to supply. And so this is more generally, like if I have, so you can ask what's the so this is this is the supply, this map. So this is different cohomology theory. Yeah, it's really isomorphism without localization, yeah. Different in different cohomology theory. And it's in particular, and in fact, it's not unique. Like this not uniqueness will account for the fact that the elliptic quantum group has all this kind of extra parameters, has this kind of there's all these dynamical parameters that is. So this is not a unique map. So what do we need from this map? So it needs to satisfy what we need instead of, so we need something needs to satisfy. It needs to satisfy the following analog. The Unbox equation. So what's the analog of the Unbox equation? Is is well, let's imagine we have three factors. So then right. Sorry, I forgot to say that this is from this picture. It's also clear where the R matrix is going to have a pole. R matrix is going to have a pole precisely when either this variable is 1 or that variable is 1. Right? I mean, this tells you in the R matrix or the inverse is going to have a pole when one of these variables, either this or that, is 1. So that's obvious from this picture. And so what is then the analog of the Unbox equation that we need to satisfy? Is let's look at an Rx3. So X3 was disjoint union over K C star Grassmannian K-dimensional subspace in 3-dimensional space. And analogous to the picture we had before is now we have a picture in principle in a 3-dimensional torus, but it only depends on the ratio of the variables. So maybe I'll draw you a picture in 2-dimensional torus. So that would be analogous to the fact. This is a picture like that. And this is a picture previously we were looking at, we would look at it when one variable goes to infinity or to 0 or to whatever. So now we have all these different zones. So we can maybe imagine like A1 is much larger than A2, much larger than A3, and then there is a situation when maybe this is where A2 equals A3, this is where A1 equals A2, this is where A1 equals A3. This familiar picture that is also underlines the Unbox equation. And so for every point in this diagram, we can record. So if I have a point A, I can record its. So for every A in this picture, consider its fixed locus. Okay? So this is so in particular here, that fixed locus here, this would be kind of x1 cubed, and here also again the x1 cubed. At the identity at the origin, we have our actual x3, and at the border between them we get, so at the border between these two, we will have like x2 cross x1. Sorry, maybe I'll try to draw it a little better. Right. And the analog of Young-Baxter equation is that when we can specialize it all the way. So maybe here more space. Here I have more space. Then here I can specialize straight to x3, or I can first specialize to the wall and then specialize here. So I have to pick. In other words, I have to pick isomorphisms between this guy and attracting manifold here, and then I take this guy attracting manifold there. And so this triangle, for every stratum in this picture, the maps, the triangle needs to commute. So instead of a Young-Baxter equation, that all these triangles need to commute. That's a requirement. So we have to pick this isomorphism so that these triangles commute, and that will be done in some. So this is some actual geometric problem, and in solution, like I said, it depends on which cohomology theory you choose. So next time we will have we'll start with review what's a covariant case here, what's a covariant cohomology, and so this would be a little bit maybe. So there'll be a review next time. So next time introduction. So next time Intro to equivalent key theory, homology, equivalent key theory. Well, let's see. What do we have in chat? Any more questions for today? Well, a question.
I have a question. Can you?
It's there's another thing, as you can think of this like the dual, like what should be the mirror picture is this sort of, like this kind of this kind of Bezrukovnikov's categories, how they attach to different strata of some stability space, and how they that's another example. There's like a dual set of examples. So this is you can ask, well, this is here I'm talking about equivalent. Here I'm talking about equivalent situation, but instead you can, this will be also a slightly equivalent situation that I have a family of GIT quotient and I have various stability conditions, then will be something like that, also a structure. But also you can more generally have some sort of variation of stability conditions, which is in particular in this sort of kind of Bezrukovnikov's world, or that's you have that sort of structure. So this is on the stability condition side. You have a variation of stability, and you have a theory. So you have a theory with you have a equivalent category on the stable locus with one stability embeds to equivalent. So you have a more specific stability condition. I mean, a more degenerate stability condition means you have a bigger category, you have more equivalent sheaf on the stable locus, on the same whatever semi-stable locus. So you have some big category on equivalent sheaves on the pre-quotient, and then you have part which is stable for one stability, part which is stable for another stability. They both sit inside the big space. More questions? To the general discussions of, I hope to come to the general discussions of the sort of interfaces later in this lecture series. But now let's just focus on things which are really kind of hands-on. Let's look at the really attractive manifolds. Well, maybe Lev, I'll be happy. It sounds like a long discussion. Maybe let's continue it. Let's maybe continue it online. I'll be happy to talk more about it, because all right, well, maybe there is the discussion group in the Telegram channel. You can always ask your questions there, and otherwise maybe we'll meet again next time.